Okay, welcome to my webinar today, November 24th, 11 a.m. Eastern. I'm going to talk about how to make your own passive AC and DC voltage probes. I've covered some of this already, but I specifically want to start with the AC oscilloscope probe because those can be kind of tricky, and why would you want to do it and all that kind of stuff. So this specific presentation is going to be relevant for people using I'm going to make this general statement, 300 kilohertz and lower. If you're working in this frequency range, this presentation will be highly relevant. It'll be very interesting and very practical. If you're interested in frequencies above that, or you very much wanting to analyze the sharp square waves, even if you're working under lower than 30 kilohertz, sorry, 300 kilohertz, then this may be interesting but not as useful. Also, so this applies both to ultrasonics and people doing audio work. So here's the outline of the presentation. So I'm going to speak about the purpose of the voltage probes. Why do we use them? And that's obviously pretty simple. I'm going to review charge measurement. Like the presentations I've been doing the last several times using a capacitor to measure charge. That's kind of the DC. I'm going to talk about the standard oscilloscope probes and actually a simplified schematic of a standard one. Also, how do you make your own no compensation probes? So the thing about this presentation is kind of focused toward making these no compensation probes. It teaches you a bit about the inner workings of the oscilloscope probe, what makes them work, what makes compensation necessary and less necessary. And also you can make these probes, like let's say you're doing 40 kilohertz transducers all day long, and you have different oscilloscopes in your lab, or you just want to simply make your setup really neat, because obviously oscilloscope probes are huge, and they're like kind of an eyesore, and you don't solder oscilloscope probes onto your circuit, but you can solder custom probes onto your circuit, and just for them to be kind of a very fixed format that can be very useful to have your own probes. I also like having your own probes because it makes you it makes you take ownership over your measurement process. Like normally you wouldn't check if your measurements are correct, or how would you know unless you try to kind of influence or interact with the system on a deeper level. So this kind of um, engages that part of the engineering, and you will own your system a bit better. And here I just give an example of what making the probe. It takes two components. It's basically a resistive passive probe. I show different capacitance measurements, oscilloscope connections, and I compare the 10x compensation probe to this custom probe that I make right here. This probe right there. So I make this, this will attach to your oscilloscope, and now you have a 10x probe with these two, and I actually test the performance of it. So that is the thing. I don't just make it and say, okay, here it is. I show that it works. So if you have any specific questions as we go on, please let me know. So the purpose of the AC DC voltage probes, well, we need to get the signal to the equipment, whether it's a oscilloscope or whether it's a multimeter. And the methods that I describe here will work for both multimeters and oscilloscopes, but mind that oscilloscopes have lower input impedance. The voltage probes that we use attenuate the signal. So if normally our oscilloscope can only work with 100 kilohertz, or let's get this here. Change the pen size. And as you see, I'm using this Ultrasonic Advisors deep purple. It's kind of funny. I made my company colors ultraviolet which is like, well, ultrasonics doesn't really have ultraviolet, but yeah, and I keep remembering I forget to put in my advertising for my consulting services now that I started weekly webinars. Yeah, I do consulting for for people developing ultrasonic transducers of all sorts and methods. I specialize in electronics, mechanical design, simulation, deep knowledge of piezo crystals, the whole deal there. So yeah, follow the links on the YouTube video or wherever you're watching this, to um find out more about my company, Ultrasonic Advisors. Um, so okay, so continuing, we're going to it can also attenuates the signal so you can measure larger voltages. So if your oscilloscope could measure 20 volts, now it can measure 200. Or if it can measure 200 volts, now it can measure 2 kilovolts. And this high voltages are often applied in anti-resonant transducer drivers, for example, for welding applications, ultrasonic cleaning applications too, I think, to some extent. We can also change the quantity being measured. So you can change voltage to charge, and you all know a lot about that. Whoever's been following my webinars, you can, if you put a huge capacitor, now all the charge generated by the piezo is getting on the capacitor, and because Q equals CV, now you have, by measuring voltage, you can measure charge right there. Also, I've also explained the concept of voltage to current with a ground side resistor. That ground side resist measuring the voltage over the resistor here, this potential difference, that tells you the current. So V equals IR. So you can measure the current if you know that resistor. So you can change the quantity being measured. It also improves the measurement bandwidth, and depending on how the probe is created, you can also improve the noise, like reduce noise. Um, Traditional oscilloscope probes are carefully designed. Now the design is probably iterated over and over again, so it's nothing new to many people. But it is there's a lot of shielding. There's resistive wire used. It's not just two components in series or in parallel, and that's all it is. There's a bit more going on. To make that whole construction, which which becomes challenging to replicate that entire process. But rather than doing that, why not make your own probes, which are simpler and don't require compensation? And I think you'll be pretty confident using for specific applications, especially lower frequency, lower than 300 kilohertz. All right, so let's go ahead and I'll quickly review the charge measurement. Now, these are going to be in the notes here. In the notes, so there'll be a link wherever you're watching this video. There'll be a notes to the link. But basically, when you're trying to measure charge, you're trying to measure charge on a piezoelectric ceramic, as far as mostly people watching my videos are interested in. So squeezing or putting pressure on the piezo preloading creates charge. And if you hook a large film capacitor in parallel with the transducer, the charge is going to get stored on that capacitor. And because if you have the capacitor in the microfarad range, and usually the piezo transducers are on the nanofarad range, you'll be dominating the capacitance by the parallel capacitor, and Q equals CV, and the charge generated equals the force times the charge coefficient. Hence, you can solve for the force by measuring voltage. I've described that a lot, and I won't get into too much detail. And maybe the folks who've been watching are familiar with, well, here's the 100 microfarad film capacitor, motor run film capacitor, and our multimeter, and we're torquing and we're getting a voltage. All right. I will go over the standard oscilloscope probe now. So inside the standard oscilloscope probe, the 10x probe specifically, because obviously for kind of a 1x probe, which does have its own problems, I'm not going to be telling you how to make a 1x probe. You can just hook wires, although that has parallel capacitance associated with it. But I'm not going to be going over the 1x probe. Typically, we are trying in our transducer systems, we're using a 10x probe, or we're using actually I have to check. I haven't compared it to a 1x probe, but Today I'm going to be talking about a 10x probe, and you can kind of take the discussion or investigation further, or just ask questions. So inside of a traditional 10x probe at the the 1x 10x switch, as many of the standard ones have, it basically shorts this 9 mega ohm capacitor to get to 1x to get for the voltage directly to go to the oscilloscope, which has a 15 picofarad and 1 mega ohm input impedance. So it's dropping the voltage um, over that kind of dissipation circuit or measurement or filter. It's actually kind of like a filter. So as you go higher in frequency, this capacitance will draw more current than the mega ohm series resistor. So that creates some types of like frequency dependence. So by adding this 9 mega ohm in series, we create a voltage divider circuit. So 1 mega ohm, we're measuring over 1 mega ohm. The total is 10. So we have a 10-to-1 resistive voltage divider. Well, that's great. But however, we also have to balance out the time constants because these impedances over frequency are not going to be stable. So the time constant of this part of the circuit needs to be balanced with the time constant here. And by adding a trim capacitor, like you have a kind of screwdriver and you put that inside of either the base or the handle of your of your probe, and you can change that capacitor value and you can do compensation. At low frequency, a compensated and uncompensated probe are equivalent. Like for DC or like 1 kilohertz or so, a sine wave. But if you're doing a square wave or if you're measuring higher frequencies, you will have definite problems. Like for example, when I had calibrated a probe for this is a 1 kilohertz square wave. I had calibrated a probe for one oscilloscope, then I changed it to another one, and this is the waveform. Now we know if you compensate it, you'll get the square wave, which basically properly represents all the frequency components there, at least as best as possible. It's not going to be perfect, and there's a bunch of non-ideal things happening. But low frequency is not relevant, especially when you get to higher frequency. It's very relevant. So you could start to mess up your measurements because you did not compensate your probe. And to do that, it's cumbersome, especially if you're using different probes. And you're always wondering, like, did I mess up the measurement somehow? Especially when 5% or 10% really matters to you. You should, and especially consistency matters, like using different probes, different vendors, different different oscilloscopes, it becomes a much like or I guess to me it'd be like a big relief to only have to not have to worry about that. So how are we gonna make our no compensation probe? Um, so again, this is a typical 10x probe, and keep in mind there's also this cable capacitance, which is actually very large, which is why which is why the 10x probe has a higher bandwidth or a faster rise time than a 1x, is because this like series capacitance here, or it's kind of parallel series-ish, it helps to cancel the overall capacitance, because if you look at things in series, the capacitance is I think it's going to be smaller than the smallest capacitance. So by reducing the capacitance, you're basically increasing the frequency response, which is why 10x probes on the 10x setting have a higher bandwidth than 1x probes uh, on the 1x setting there. So how do we get to a no compensation 10x probe that we don't have to change anything for? And as you'd expect, we have to probably make some we'll have to make some not compensation. We'll have to make some what was that word? Something concessions. You'll have to make some concessions. So this is like a 10x concession probe. Okay, we're gonna lose some bandwidth, but we're gonna gain consistency, which is also very extremely important for engineering work. So for the 10x probe, we have this 10 mega ohm to 1 mega ohm, you know, times 1/10 when we get to the oscilloscope here. I already showed the typical 10x probe, but now for the no compensation probe, we're going to have a 100 kilo ohm series resistor, not a 9 mega ohm, and we have an 11 kilo ohm, excuse me, 11 kilo ohm parallel resistor we added. So now we're effectively reducing the input impedance of the oscilloscope. And I'm gonna have to cough again. Hold on. So we add this parallel resistor, and it it reduces the input impedance, which is actually not good. Traditionally, we don't want that to be low. But by putting it low, we are controlling that we are making the time constant very small. Because if the RC, because for the RC time constant here, we are effectively shorting this capacitor by this 11 kilo ohm. So it's very small. And also this 100 kilo ohm doesn't have any capacitance associated with it, sort of. There is this cable capacitance now that we're not explicitly accounting for. But if you do wind your own wires, they will not be so intimately touching each other. So this is a bigger capacitance and I do this smaller. So this is a smaller capacitance. So there's still capacitance there. We're not compensating for it, but it'll be smaller in size and will be basically within our frequency range will be dominated by these very low time constants. And although the time constants will be many times different, or the percentage different will be high, the difference in seconds will be very small. That's why at DC frequencies the time constant doesn't really matter because, well, it's not relevant. It's very, very large. According the time constant difference is very insignificant with regard to the frequency being measured, which is DC or low frequency. So in this case, because the absolute difference in time constant is small, um, we don't have to compensate. So here we have 110 kilo ohms total, and we have an 11 kilo ohms at the measurement side, so that's 0.099. So in any case, like so what you can always do, so if you get this will also work if you have a 200 kilo ohm, and then you have that, and then you connect it to a 22 kilo ohm. If you have a 100 kilo ohm and you connect it to a 11. I noticed that this ratio always ends up being 0.9, actually like 0.09 at this point here, because 22 divided by 222 is a 0.909. It's not the same if you have 200 and then 20 here. So this extra 2 kilo ohms or extra 1 kilo ohm here, that helps to get this very close to 1. And practically that's what we're gonna have for our 10x probes anyway. They're not better than that kind of accuracy. So again, what about the time constant? Well, because the time constants are just really small now that we've added these resistors here and everything, we don't have to worry about the max time constant. It's limited. So you don't need a compensation capacitor, and you can move freely in your probes. You can also design your 100x probe if you wanted to. So if you had your 200 kilo ohm, and then you could do a 2.2 kilo ohm. I think that I think that would work properly. But basically you can do these ratios and you can still get I have to check the ratio again. But you can use two components and now you have a 100x probe. Or you can do a 5x or whatever you'd like to. You can build all of your probes into one breadboard. Are there min or max values? So these are going to affect the frequency performance. I haven't investigated that experimentally because it both the bandwidth both has to do with the ADC and the input circuitry that we're attaching. But there are technically no minimum. Oh, so this is the important thing. That's a great question. The minimum maximum. I didn't address this. So when you're measuring your piezo transducer and you're measuring with the voltage probe, um, it sees um a probe load. And it dissipate so you're going to be loading the circuit basically. So this does two things. So the probe is going to both one, it's going to load the circuit. So it's like in this case, for the if you like you loaded it for the traditional 10x probe at DC, you're loading it with 10 mega ohms, which is not bad, right? At DC though, keep in mind. So hey, that's not going to disturb the circuit. That's one thing. You don't want to load because there's some circuits that you don't want to load, especially and also you could mess up the measurement if you do the probe itself by the input impedance. So if you're trying to measure a 100 kilo ohm, oh, I'm pressing the button, anti-resonance, and I'm giving you 110 kilo ohm input probe like this. That's a bad idea. You're going to be you're that you're not going to be able to measure that properly. It's going to drop voltages because your probe is going to be now the circuit thing that you're trying to measure is now part of the measurement circuit. So the higher the input impedance of your probe, the better. But I'm taking advantage of the fact that, hey, let's say we're trying to measure impedances 1 kilo ohm and lower. Like we're trying to measure resonances, and many people there are trying to just measure like 1 kilo ohm and lower, or 100 lower than 100 ohm measurements. Then having a 110 kilo ohm loading function is just fine. It won't disturb your measurement. It won't drop voltages inordinately. And you can do circuit simulations. There are also like calculations about how much voltage is being dropped because of what you're trying to measure. But you should not do this type of probe for anti-resonance measurement. It's mainly if you're focusing on resonance, which many of us are, then these probes would be good. You can also increase your input impedance. Like you could use a 1 mega ohm resistor, and then you could use a 100 one you can use an 11 kilo ohm. And this would give you a 100x probe. Uh, and the reason I'm using 11 kilo ohms instead of 110, so why not just use 110 kilo ohms and make a 10x if that's what actually kind of what you want, maybe. The reason is because that this capacitor here and this mega ohm is still part of the circuit. So although you put like 100, if you put 100 kilo ohms in parallel, you're actually not gonna get 100 kilo ohms dominating the input impedance. You're going to get 1 mega ohm in parallel with 100 kilo ohms. It's not going to it's going to be, I don't know, like let's say 90 kilo ohms then. So you're not going to be, but by choosing a low input impedance, you're dominating the input impedance and you're saying this is what it is. It's not changing from this because I set it to be such a low value. So you're making a sacrifice. You're doing what did I say? You're doing a compensation. In order to avoid compensation, you're doing consequent. I forget that word. Uh, you're making a sacrifice there. But it's for many applications. The simplicity of having everything on all your probes on one circuit board or having those components embedded inside of your system are worth it. So yes, so you have to understand what you're measuring. And most people besides Hussein Shakani of Ultrasonic Advisors, most people are measuring one type of device and one type of operation. They're measuring a Langevin transducer or an atomizer at resonance, and you know the impedance values, they're not going to be 100 kilo ohms. So you are fine to design such a such a probe and use it indefinitely. Um, if you're measuring all over the board, all different types of impedances and frequencies and resonance and anti-resonance, and you care about everything, then that's going to be a bit more tough for using a standard probe. But yeah, I invite you to be kind of creative. You can put trim capacitors here, but I don't particularly recommend it because then it starts to get complicated and the simplicity factor is lost. Um, so here's a simple thing how you make the probe. So I use a strip board, and you could obviously fabricate it with a PCB, traditional manufacturing. You could do it on traditional breadboard. You can just do it, the dead bug style where you just solder things directly to a BNC connector. This is one idea. So these are like kind of male right angle pins. I solder that onto the strip board where these lines are automatically connected with copper. So it's called like strip prototype board, and you can cut it with a tin snip. Um, then I put two of the angles in each connector. And this is the wrong connector. I use a different one. Yeah, there I use this one. So then I solder it, and these two sides are the same anyway. And this is the 11 kilo ohm over the input. So I have the over this input I have 11 kilo ohm, and that is always going to be much larger than that 1 mega. And behind here on the oscilloscope we have 1 mega ohm, and we also have that like 15, and we don't that like which can vary, the 15 picofarad input impedance, which is what we compensate for. Here I put in the 100 kilo ohm impedance, and I think if I'm looking at it correctly, this is going to be the positive or the measurement side, and this is going to be the ground side. And this is it assembled again, and this is I attached some wires to it here, and I just kind of put a magnet wire wrapped around it for a strain relief. Which is, and this is, I just assembled with what I had on hand. I just put a piece of tape on it and I wrote what it was. Sorry. Isn't get not getting more complicated than that. All right, now the capacitance measurements are of particular importance to understand the frequency dependence of the input. So here we have the LCR meter without anything connected, 0 picofarads. I zeroed that. And here we just have wires sitting in there. That's 16 picofarads. Here we have just that connector, and just that connector, if this doesn't freeze again, it's 3.7 picofarads. So it's not very high. This is interesting. So this is I believe it's I think so. This is the 10x probe. This is the probe I just made. This is the probe I just made. This is the custom probe, and at 10 kilohertz, it's 110.84 kilo ohms. So this is the custom 10x. This is this is the standard 10x. And the funny thing is, the standard 10x at 100 kilo at 10 kilohertz is 245 kilo ohms. So be careful measuring your anti-resonances with normal probes. You may need to use a 100x probe with the 99 mega ohm series resistor, standard one. Yeah, so just know that you don't want to be measuring anti-resonance or very high anti-resonance with a normal probe if you don't use some type of rectification after that. Yeah. Okay. Yeah. So somebody asked a question about they try to use this a regular crocodile, like they had the BNC to clips, and you found this was very noisy. Yes. So the standard oscilloscope probes, they have like resistive wire, and they have great shielding, so they're designed really well to get rid of noise. That's and the normal BNC to crocodile, they're terrible with noise. It's better to use a 1x probe. Use a 1x probe to measure in the 1x setting. So you can use 110x, but use a 1x setting. That will help you with the noise. But as far as this custom probe goes, it already has kind of a noise reduction built in because of the low input impedance. The noise is basically very high. It's very high impedance signal. So if you are running it and you're putting it over a 2 kilo ohm resistor, you're gonna just kill it. So it will not exist. It will not be there anymore. So I think the resistor method that I'm showing will help with that. But if you just don't want to use a custom solution, just use a 1x probe, not a BNC to clip. They're terribly noisy. But you can use things like averaging and stuff, or you can simply, if you want to, you can use you can just you can put like a BN you have the BNC, and then you have the red alligator and the black. It might work if you put like a hundred, you just put 100 kilo ohm resistor in parallel. That might do the filtering for you, so you don't have that. Yeah, if you're measuring small signals, that's also challenging there. You don't want to attenuate it any more than you have to. In general, benchtop oscilloscopes have a much better lowest amplitude capability. So the picoscope I have has I think 20 millivolts small scale. I think like benchtop oscilloscopes have like a 5 millivolt small scale, so that might be another option if you want to attenuate to get better system performance. But you still want to be able to properly measure it. You may just use a 10x probe like that, or and because this method I'm showing today, it requires attenuation, and that's kind of what it's for. For 1x measurements, even if you want to do something custom, you may just put a 100 kilo ohm in parallel, because that's still going to get you 100 kilo ohms. Like you have the 1 mega ohm here, and there's a 15 picofarad inside the oscilloscope, and then you have the 100 kilo ohm, and all these are in parallel. Like you're not dropping voltage anywhere as long as what you're trying to measure is, let's say, 200 ohms. You're not going to be hurting anything by putting a 100 kilo ohm there. And hey, you could put an extra capacitor too if you want more filtering fun. So there you go. And this is the capacitance of that. It's 64.96 picofarads, and I believe this was for the 1x setting. I can't remember. So I think that was for the 1x setting. This was for the 10x setting. So when you put it on the 10x side, you put that series capacitor there. Now your capacitance reduces to about 18, or I think 25. I'm not sure which one is correct here. I would say the 18 one is correct because I put that probe directly in there. I think I lost the tip. And for the 10x probe, so for the 10x probe at 10 kilohertz, you are at 842 kilo ohms. So it's not blameless. Now when you're getting to the 40 kilohertz, 50 kilohertz, 60, you're gonna see some lower. It's not 10 mega ohms anymore. It's not 10 mega ohms at all. It's deceptive, like saying, oh, the input impedance is 10 mega. It's not 10 mega ohms because that capacitor, even that small capacitance, is doing harm. In that sense. So you have to be aware that your measurement system's always affecting it. And this is why it's great to have your own probe, because you are aware of it and you designed it in there and you know it sucks. I'm just joking. So it's like there's like issues. Otherwise, like you have this long oscilloscope probe, which are very standard. Obviously, so this is how so the oscilloscope that I'm going to use for testing is a picoscope, USB oscilloscope. It doesn't have a very powerful wave generator, so that could lead to part of the solutions or answers I'm gonna get today, but I basically, in a very crude way, hook it up to the arbitrary wave generator, and this is the how I hook the 10x probe, and this is how I just unfortunately jammed everything in there. So that was my circuit. Sorry about that. Then also the nice thing about custom probes is you can make the probes as short as you want. What's so good about making shorter probes? Well, they have less capacitive loading. That's what's great about it. Because a lot of the capacitance loading comes from the probe length, the wire length, and also a lot of the annoyance comes from the wire length too. Of using these long probes when you have 4 of them, no, I don't think you have to repeat ground everywhere, but unless you're doing some RF stuff, which we're not talking about that today. So that's how I hooked it up. And let's go to I think I showed this already. This is the 10x probe compensation. So this is how the probe was. I probably already compensated for a different for actually the analog digital discovery, which does have explicitly different um input capacitance. But when I changed it to the picoscope, it looked like this, which is I didn't see the I didn't record the effect what that would have on like 100 kilohertz or 50 kilohertz, but it certainly is not stable. So I fixed it. I changed you turn the screw, and you even out you properly compensate, and you have a good square wave response for the and that was for the standard probe. So this is a square wave comparison. So we see the red here. The red is a standard probe. Standard 10x, and the blue, that's not how you spell blue. Okay. And the blue is the custom. So I guess my probe fell short. It didn't have the as close to a good of a rise time, but I will show you later. The square wave response was very good. It looked like it was compensated. So if you were to zoom out and look at this blue probe, or the custom probe, you would not see you would think it was compensated. I just forgot to put a picture of it, I guess. So this is zoomed into 1 microsecond per division. All right, any questions here? Okay. So we do want to understand bandwidth, and I did find that like just looking at bandwidth and rise time wasn't good. So I measured the rise time for the it was for the 10x probe for the standard to be 80 nanoseconds, and for the custom to be 170. So it's about twice as slow, or the bandwidth will be like half, I guess, in that way. And there is the basic like, well, the bandwidth times the rise time equals 0.35. And that gets you to a bandwidth of like 4.3 megahertz for the 10x probe, which I don't really believe. That seems like it's too small. So what I did basically, and because this generator gives you ability to go up to 1 megahertz. So I did the sine wave method, which now the generator is not like it's not low impedance, so it's not gonna like driving 1 megahertz, because the input impedances of the probes will now drop to the kilo ohm range. They're already at 245 800 kilo ohms at 10 kilohertz. Now at 1 megahertz are going to be a lot worse. But I just went with it. and just to give an example, because this is the worst case scenario I'm showing today, because the probe that the 10 megahertz probe is advertised at the 10x probe is advertised at 100 megahertz, and the oscilloscope is 25 megahertz. So we're not going to get 4 out of this system. So this is just the worst case scenario. So I want to show, I forgot to show one other thing here. And that is the peak to peak values. So my custom probe, channel A, so the custom probe got 3.952 volts. It should have been 4 according to the a generator output for peak to peak voltage, and the peak to peak for the standard probe was 4.037. So I'm not sure which one is right, but they're certainly different. And you can compensate for this. You could also like be very particular and put the exact right resistor for this system if you wanted to have everything very repeatable. I don't think they go through all that trouble for your standard 10x probes. They probably just put a 1% film resistor in there and call it a day. Because there is but getting back to this part where I just want to get an idea about what frequency range I could use. I know that my generator is not ideal for this. I already had interesting results from this part from the rise time, but this is like a worst case scenario. So we started at 10 megahertz, 10 kilohertz. So this is 10 kilohertz, and I did the amplitude. So the amplitude of the standard is here. Sorry, the custom and the standard. So the custom is 3.952. The standard is 4.037. So I wanted to look at where it goes where the amplitude drops 5%. Because engineers love 5%. As long as you're 5% close, like nobody asks you like, oh, how accurate was the measurement? Oh, it's like 5%. If you say 6, they'll be like, but you say 5%, you'll save your skin from further investigation. So where did I find it to be? So at 100 kilohertz, it's at 3.873 and 4.037. So you see channel A, the custom starting to drop. It isn't 5% yet. At 300 kilohertz, at 300 kilohertz, um, and mind you, so I'm measuring these at the same time. So if there is voltage drop due to the probes being hooked up together, due to any of the probes, they will both be measuring that voltage drop over the output impedance of the generator. So we don't have to worry about the generator dropping in voltage because we're doing the same amount, but I did not consider that. I didn't consider the delta. Anyways, I just this is a kind of a test here. Anyways, so at 300 kilohertz we have 5% reduction in amplitude. So this means up to this frequency, we're in pretty good shape for our channel A, or basically the custom probe. Um, the the standard probe goes to 1 megahertz before dropping 5%. And probably maybe part of that drop is going to be due to this the other probe reducing in impedance and basically drawing more current. So yeah, I could probably look at the delta between these two and get a better representation because I don't have a perfect measurement of the source. But yeah, that's how I compared it. So I would say from this analysis, I found that this probe, which was the 100 kilo ohm, okay, the writing's happening a little bit slowly right now. The 100 kilo ohm, with the 11 kilo ohm, it's good to 300 megahertz. 300 kilohertz, and it should be good. It should be very good for resonance measurements. It will at least tell you where the anti-resonance is, and the input impedance is going to be 111 kilo 111 kilo ohms. And then I believe the nice thing is that it should not drop below this, because no matter as long as if you have your wires, I think most of the capacitance is probably going to come from the junction, not the wires, because the wires are not necessarily like bound together and they're pretty short. So because we have this impedance there, whatever capacitance happens after that resistor, it's not going to be seeing much voltage. So I think it will definitely limit the current or the impedance seen I haven't done frequency sweeps and stuff over that, but this is just I guess show and tell. And this is my analysis. So I will stop the recording. I almost thought I forgot the recording. I'll stop it and I'll ask if there are any questions.